Hello everyone and welcome to this TU-Automotive webinar. Pleased to be welcoming you all to the Eyes of the Autonomous Vehicle. My name is Jamie. I'm a project director over at TU-Automotive and I am specializing in our ADAS and autonomous side of things. Very pleased to welcome our two panelists today. We have Radovan Muick. He's a technical specialist at Changan, United States R&D Center, and Philip Dubose, marketing director at Texas Instruments. We'll be handing over to them in just a second for their presentations, but I very briefly wanted to take you through the format of today's webinar. Before we get to that, this webinar is being run in conjunction with the TU-Automotive ADAS Autonomous Vehicles USA event, taking place on October the 2nd and 3rd in Novi. If you're interested in all things ADAS Autonomous, this really is the event for you. If you have any questions, visit the website or please email me after. But let's get on to the topic today. We will be kicking things off with Radovan. So, Radovan, I'm going to hand things over to you. We will just be swapping the screens to you now, and take it away.
All right. Are you able to see my desktop?
Yep, we've got that there. If we can just put it in present mode, that's perfect. Away you go.
Okay. Well, thank you very much for joining this webinar. My name is Radovan and I work for Changan. Changan is a large Chinese OEM, and we do produce vehicles, and we are very interested in researching connected and autonomous vehicle. So with this presentation, I will start first with an overview of the stages of autonomy according to NHTSA. So the level 0 automation, there's no automation. The driver is completely in charge. Level 1, and it means that a single control, such as braking, lane keep, or speed control, are automated. And again, the driver is completely in charge of the vehicle controls. Level 2 is combined function automation. So more than one control is automated. Driver is still very much responsible for driving the vehicle, and it's expected to be available to take over on a very short notice. Level 3, it's limited self-driving automation. Vehicle take control most of the time. Driver is expected to occasionally take over with a comfortable transition times. So things like highly autonomous driving on a highway would fall into the level 3 stage of autonomy. And then finally, level 4, full self-driving automation. In this stage, vehicle completely drives the vehicle, and driver is not expected to take over at any time. Now, as far as the requirements for these levels, they vary significantly. So for level 2 and especially level 3, the transition of control will be very critical, and it will be the solution that are provided for level 3 and level 2 will be very, very much human-machine interface intensive. For that, we have to have driver monitoring. Driver monitoring will need to kind of assess the state of the driver when the transition of the control happens, and then the vehicle will have to kind of communicate properly to the driver. So whether that is a active force throttle, active force pedal, or it's a heads-up display, or some other modalities of warnings and kind of transferring the information, maybe haptic steering wheel or haptic seats or haptic seat belts. There has to be a very nice communication between the intention of the vehicle to hand over the control or a driver to engage and disengage from the control. So when we talk about the eyes of the autonomous vehicles, we have two modes. We have sensors and stuff that is kind of looking outside of the vehicle, sensing the environment, and then we have sensing inside of the vehicle, sensing what is the status of the driver, and so on. So for driver attention monitoring, so we're thinking about like the industry as well, a camera-based solution. So what will the camera driver attention monitoring system do? Well, it will detect the drowsiness, fatigue, distraction. It might look for health monitoring. It may be used for security, maybe personalization, and it will definitely help in this controlled transition between the autonomous and manual driving. And it may also help in false alarm suppression. So, for example, if it's more of a warning type of system, if a vehicle is about to warn the driver, but the driver is actually paying attention to the threat, so the vehicle does not need to warn the driver very intensively, and so on. What can it do in the future? The research is ongoing to do a driver intention, or maybe detect the driver mode, and so on. Why camera? Camera is a very low-cost device, highly available, it's compact, it's easy to research and develop. Of course, there's lots of issues with camera. If a driver is having sunglasses, camera placement, user acceptance. So, for example, if to enjoy the autonomous features, it's unclear how likely the drivers are to pay the price of being monitored. There's maybe a different ambient light that can present a problem, and so on. How driver monitoring is implemented, it is lately starting to be utilized using artificial intelligence, neural networks, but also it can be implemented in classical ways to detect face, eye tracking, head pose, eyelid estimator, and so on. Okay, so now I want to talk about the sensing outside. So our philosophy in Changan is to put as many sensors as possible in prototype vehicles, and we kind of divided the sensors into three categories. The first one is to do environmental perception. So for that we can use a number of LiDARs, maybe 4, 6, or we will also use a high definition LiDARs with 64 lines or so. We're also using radars, long range radars, medium range radars, and short range radars, maybe on a side to detect oncoming traffic. We're also heavily using cameras, and we may have anywhere from 4 to 8 cameras on a vehicle. The cameras are kind of looking forward or looking on a side, looking for a blind spot, and so on. And then traditionally we have been using ultrasonic a lot, because that's a very inexpensive sensor, and it's easy to integrate it into a vehicle. However, if in these sensor suite we have a lot of redundancy. So our goal is to put a lot of sensors, do a proof of concept type of work, and then work towards reducing the number of sensors to a more production levels and types of sensors and so on. So another type of sensors would be used for localization. So we're looking at high definition maps. We're also at the moment with our prototypes, we're using a high grade inertial measurement units, as well as differential GPS receivers for high accurate localization. And we also have communication sensor suite as well. For this, we are utilizing the DSRC, and we're also having a cellular connectivity to the prototypes, and we're interested in satellite communication as well. And these communication modes have different purposes. For example, DSRC is used at the moment for warning applications and for things that are around the car, and typically for immediate warnings, and not necessarily for downloading the maps and so on. Cellular communication is more used for that kind of downloading the maps, updating the maps, providing the GPS corrections to the DGPS receiver, and so on. So why camera for environmental perception? What does it do? Camera detects lane marking, lane widths, kind of road features. They also can detect signs, stop signs, speed limits, traffic lights, and so on. It can detect static objects such as walls, buildings, and poles. It can detect moving objects, vehicles, pedestrians, and so on. So what will be done next, what will be researched, will be perhaps doing a sensor fusion of camera with other devices, radars, LiDARs, and DSRC, and it may help in localization and so on. Why camera? It's low cost, high availability. There's many mature suppliers. The software and hardware is mature, and that's kind of one of the benefits of a camera-based solution for environmental perception is that it has very good azimuth angle measurement compared to radar, for example. Now radar, on the other hand, again detects the static objects, buildings, poles, walls. It can also detect moving objects, vehicles, pedestrians, and so on. What is the R&D in the future? It can be a part of, again, of a sensor fusion suite. Why radar? It's relatively moderate cost, high availability, mature solution and software, and it has accurate distance and speed measurements compared to camera. Camera has good azimuth angle, and radar has a very good distance measurement. So in sensor fusion, these two sensors will kind of give their best to provide a better perception. Okay, so the next sensor we're looking at is a LiDAR, and we also want to use that for two things. We want to use the LiDAR for environmental perception, meaning find out the vehicles, roads in front of us, and also we would like to use LiDAR for precise localization. So what can be done in the future with LiDAR? Again, it can be a part of a sensor fusion, and it can be a kind of one of the leading sensors in sensor fusion solution, because LiDAR, in our experience, have been the most accurate sensor. And there's various type of LiDARs. There's a high-grade research LiDARs with 64 lines. Some people are working with 120, 128 horizontal lines. We're kind of investigating what is the minimum level of kind of performance of the LiDAR needed for autonomous features. We're also interested in fusing a LiDAR with a camera to enhance the performance of a lower grade LiDARs to the performance of a higher grade LiDAR, but with cost savings, of course. So why LiDAR? LiDAR is very accurate sensor. It has a very relatively long range detection. It works in many challenging weather conditions, and the industry is moving away from a kind of moving parts and mechanical parts towards a solid state, which kind of there is a promise of lowering the cost for production systems. Okay, and then we come to the vehicle to V2X, or vehicle to everything. So for V2V, what it does is, like I mentioned earlier, it's mainly based for warnings. For example, EEBL, or electronic emergency brake light, forward collision warning, do not pass, blind spot, intersection movement assist, and so on. Also, the V2X, based on DSRC, can do a vehicle to infrastructure applications such as signal phase and timing and map type of applications, curve speed warning, sign violation warning, and so on. Why V2X? Well, it's relatively inexpensive hardware, and it works off of the 802.11 chipset. It has a relatively long-range detection on 300 meters or more. It works in all weather conditions, and this is currently the only non-line of sight sensing technology. It's on the path to be a mandated system in the US. It is tested and proven. It has been in hands of OEMs and Tier 1 suppliers for many years. And what can be done in the future? Perhaps a vehicle to pedestrian application can take off. It can be used in platooning, in cooperative adaptive cruise control. It can be have more application on a V2I side, and it can also be part of the sensor fusion suite. Now, as far as machine learning, now perception can be implemented using the neural networks, artificial intelligence. And why we are interested in machine learning is because using machine learning can bypass the complicated math that is involved in traditional methods of doing object and feature detection and tracking and classification. It can potentially be faster to implement if there's enough training data available, label training data available. It can potentially have similar or even better performance than the classical methods. And what the challenges are with artificial intelligence is validation and verification. So we do know that it works, but we are not necessarily able to always pinpoint if it fails, why it failed. And it can be very, very difficult to debug. Now, as far as like sensor suite, we are having all these different sensors as an input: radars, cameras, ultrasonic maps, GPS, DSRC, CAN, vehicle information, and so on. And we can do, traditionally it has been very distributed functionality in the vehicle. So we can have two options. We can have a sensor fusion done on a object level, or we can have a sensor fusion done on a much lower level with raw data, for example, raw point clouds from LiDAR and raw returns from radar and so on. If you do low-level sensor fusion, that will actually require a much more powerful processor, and it will be more centralized or unified controller. So this unified controller has to do sensor fusion, detects pedestrians, vehicles, lanes, do the tracking, perform awareness functionalities, path prediction, route predictions, control the human-machine interface, and also control the vehicle. So this computationally is very, very intensive, and communication is a big deal here as well. And on the right side, you see at the moment how our prototype vehicle looks like. There's a lot of equipment in the back, and that will be all shrinked into much more powerful ECU. So 16-bit, 32-bit controllers is not it's not going to cut it for this kind of functionality. All right. So with this, I will end my talk.
Radovan, thank you very much. That was an exceptionally concise overview of where we are with sensors right now. So we'll be handing over to our next presenter in just a second. I just want to remind our audience that if we have time at the end, we will be taking questions for the webinar. So if you want to submit some questions now, we'll be putting those to the audience very shortly. But for now, I'm going to switch things over to Sudip Dubose from Texas Instruments.
Jim, is my screen visible?
Bear with it 2 seconds. I think it's coming through just now.
Okay, so while we wait for the screen to come up, the other one talked about sensor fusion, sensor suite, what's optimal, for a car of the future, levels of automation. I'm going to talk about the humble radar, right? Essentially talk about the trends in the industry that we are seeing, and end it with a note on what TI is doing towards those trends. So let's start with this picture, right? The reason I like this picture is it kind of highlights the heterogeneous nature of the objects or the scenes that a future car will have to navigate through. And the sensors, you can call it eyes of the car, or essentially sensory organs of the car. It needs to navigate through scenarios where it has large objects, small objects, various different profiles, different velocities, and these profiles can be different in azimuth and vertical, and detect each one of these in a way where it essentially can create a navigation path among these objects. So the sensors that we have today, Radhavan talked about vision, talked about LiDAR, talked about radar. Each one of these sensors have to go through a step function in terms of what they are capable of in order to realize this vision of machines and humans coexisting in the same space, really the vision of intelligent machines. So now if we drill it down to radar, right, and again going down the line of growing sensing needs, for any sensory organ in the car, and I'm using the organ because we are getting to a point of the realm of artificial intelligence for a machine. It needs to detect distance, angle, and velocity. Right? It needs to place the object in a 3D space, and while it allocates a coordinate in the 3D space, it needs to classify the object and try to essentially differentiate it between predefined classification that machine learning has given the sensor. Like a very simple example is distinguishing between a pedestrian and a trash can. Similar reflectivity, similar positions in the road when a car drives close by to a pavement or a driveway, but totally different levels of criticality and behavioral when it comes to movements. The sensors need to coexist in a way where the automotive industry can adapt them easily. And it gets to a point where it should be easy to install in a car. It should not totally change the way human beings are used to seeing cars. You see a lot of autonomous vehicles driving around, and the challenge that the industry is trying to solve today is the challenge of sensing and compute. But very soon we'll get to a state where the challenge that the industry will have to solve is to package this sensing suite in a way where it looks more like a normal car. So that's why I put this topic of penetrate surface, where you can make the sensors a lot more discrete. The sensors have to be really resilient. Driving conditions are not always the ones that we have when we demonstrate a technology, right? In a real life scenario, think of a street in Beijing, Tokyo. Think of a crowded metropolis where, in a rainy day, the sensing needs can be very challenging. Different stages of lighting, aggravated with the presence of rain, snow, fog. It cannot be an excuse for a self-driving car to say, I'm going to give up, and the human being has to drive. Self-driving technology will be tested where it's most needed, and the most needed scenarios are when the driving becomes really difficult. So if you look at all of these, microwave, right? We use the word radar, but essentially it's millimeter wave microwave reflection. That really is the only sensing technology that can meet all of these three needs at some degree. And the reason I use the word only sensing and able to meet all of these needs is, if you just take these needs of detecting range, velocity, angle, or stay behind plastic, or resilient to rain, fog, and dust, there can be options where you attack just one of these aspects and build a sensor. But if you really want a sensor, which is kind of your last sensor standing in a highly automated car, microwave is the resounding answer. And this is not just a view of Texas Instruments. This is essentially, plain physics. Right? It's RF. It can do a lot better compared to optics, given different situations. So with that in mind, let's look at where the radar sensors are today. And Radhavan showed a few pictures when he was presenting. If you pick up a sensor that is available for mass production today, in terms of resolution, in the straight line, you'll get something in the range of 70 centimeters. You hardly get angle information. So these things are essentially car detectors. It will tell you if there is a car in front at a certain distance, and will either control your speed or hit the brakes. That essentially is what the feature set is. It's a basic car detector, presence detection. It's good enough for warning and braking emergency braking. Those things are available in quite a few segments right now. These sensors tend to blind each other when they are working in close proximity, and this is where the entire topic of interference comes in. If you have too many radars operating in close proximity, think of 10 years from now, 50% of cars have radars. Each one of them have 3 radars. If you can recollect the diagram that the other one showed, that's a lot of interference in close proximity, and that can cause errors or just false detection. Radars today are typically a single function. You can do a blind spot, or you can do a ACC. Having a radar which can be repurposed dynamically depending on the driving situation of the car is not something that's present yet. And these sensors are big. I had a sensor in my hand when I went to the same slides in telematics a couple of weeks back, but if you pick up a radar from a car tear down, these are not objects which are easy to install and maintain. So if that's today, and if we look at the vision that we have for for the radars of tomorrow, resolution needs to be less than 5 centimeters. If all that you can resolve is 70 centimeters, that's like merging a trash can and a pedestrian into the same object, or a bicyclist and a bus behind it into the same object. The angular accuracy has to be less than a degree. It really has to measure exact velocity and spatial distance. Classification is required. You need the radars to be multimode. Multimode meaning the sensors can be reconfigured based on the driving situation of the car. And last but not the least, these things have to be small and extremely low power. Cars in the future will mostly be electric, if not all electric. Energy efficiency will be a topic. Weight of the car will be a topic. Then comes the last challenge of mechanically fitting all of the sensors in a thing that still looks like a car, to make sure that the common masses, you get the appeal of the common masses for buying these cars. So if you look at these two requirements, this is not a simple evolution. This is a discontinuity, and the reason we title the presentation the way we do is the existing technology that is used for building these high-frequency microwave sensors, silicon germanium to be specific, it will not be able to bridge this gap. So when we say it will not be able to bridge this gap, the question comes, what is the answer that the industry is looking at? And Texas Instruments is not the only one pushing this envelope, but I'll talk about specifically what is it that we have done. The challenge that the industry always had was building a transistor which will operate at these high frequencies. And we're talking about 77 and 81 gigahertz frequencies. These are way up in the mm wave range. It's not easy to build this with standard CMOS. But once you get to a standard CMOS at these frequencies, you can add all the extra features or smartness that is needed to make these high frequency circuits operate in a way where you can get from the red board to the blue board, right? So the challenge really has been, how do we get it to a mass production standard CMOS, which will enable the integration and smartness and low power that the sensor portfolio desperately needs. So I start with ITRS graph, which talks about the trend that we have seen in the last decade almost on FTF max of CMOS versus silicon germanium. And essentially the graph drives home the point that the industry is at a stage where investment in high frequency CMOS can and will return benefits. So if I go to the TI specific investments that we have done, we had a project in the TI Advanced Lab called Kilby, and it's named after Jack Kilby, where we said, let's squeeze all of this into one single chip. Everything, right? The antenna, the baseband, the processing, all of that into one single chip, and see how far we can push it in frequency. So this experiment, trial, research that was done, tried building a 160 gigahertz radar sensor in a single chip. So you see various views of the package. On one side you see the silicon, on the flip side you see the antenna. So this on a PCB, on a standard FR4 PCB, will build a sensor which can see, let's say, 10 to 15 meters. And the success of this gave birth to what inside of TI is now the 77 gigahertz radar portfolio. So we went through a couple of phases. The next phase was translate from 160 to 77, because that's the frequency band the automotive industry wanted to use. Same approach. We had antennas on the package, 2 transmit and 4 receive, standard FR4. This was again a successful completion of the phase, and with that, early in 2016, early in 2016, we started sampling what we inside of TI called the AWR portfolio, and essentially get to a point where we can offer the industry, our customers, the means to enable a sensor which is the size of, let's say, a smartwatch, consumes an average power of a few watts, and can enable 4 to 5 functions in that box for pretty much every sensing need around microwave that I talked about in the last few slides. So that's what I had to present today. Thank you.
Okay, fantastic. Sudipto, thank you very much. Please say we've got a couple of minutes for questions. So Sudipto, if you'd like to stay on for a second, I'll put this first question to you. We've got about 5 to 10 minutes to get through this. So the question is, how has the integration of these new sensors changed the life cycle of the vehicles they are going on? Does it take longer to design? Does it take longer to pay back so the vehicle doesn't get a redesign as often? Sudipto, we'll stick with you for this question, and Radhavan, I'll bring you in just a second.
Yes, that's a great question. So think of a vehicle as like a smartphone of today, right? And I think that's a great parallel in my mind, because once you build or buy a smartphone, you do not want to stay with the same OS and same feature sets throughout the life of the smartphone. I don't believe that we will be changing vehicles at the same speed at which we change our smartphones. But if you think of the future of ride sharing and fleets, where personal ownership reduces and you are actually renting and leasing a lot more than you do today, you would like to have a sensor suite which can keep up with the needs of the industry. The point here is, as you bring in CMOS technology into these kind of sensors, you can build in a lot of programmability which can be used in deployment of the sensors to actually change the way they're operating or enhance their functionality. I think of it as an OTA, over-the-air update, where next day morning after you do a firmware flash of your car, you have 3 more new features.
Okay, thank you, Sudipto. Radhavan, we'll bring you in here. Have you got any thoughts on this?
No, I think I agree with Sudipto.
Of course, nice and easy there. Radhavan, I'll put this next question to you then. So the question is LiDAR necessary for localization, or can we get by with camera and radar with localization in all weather conditions?
Well, that's a very, very good question. LiDAR is actually the best we have so far. LiDAR is expensive and has durability issues, but as far as accuracy and range, the LiDAR is the best sensor. Now, it will be a balance between the kind of what do we want? Do we want the best accurate sensor, or do we want to save cost? So that's a very, very tough question to answer directly. I can just say that I'm hoping that LiDARs will become cheaper and we'll be able to use LiDARs for both localization and environmental perception.
Okay, fantastic. There's quite a few questions coming in. So, Sudipto, rather than pass that one over to you, there's a question directly relating to radar that I'd like to put to you. So, the question we've got is, with the radar technology you're working on, what sensors will become less necessary? And ultimately, do you think that radar could potentially replace LiDAR?
So, yes, that's a question that I think is I wish I had a cent for every time I got this question. But anyways, radar will replace a few sensors for sure. I don't see ultrasounds surviving for a long time. I mean, ultrasounds have been there, will be there, but in terms of investment or disruption in ultrasound, those will slowly get weeded away as radars get smaller and can do the proximity sensing that ultrasound are essentially doing today. And it's really a cost and size function. When it gets to LiDAR, camera and radar, the future is fusion, just as Radhavan pointed, right? There is no one sensor that's gonna supersede the others. Each one of them add their own values. But if you look at the cost aspect of it, as the various cars get rolled out and they have different sensor suites depending on the level of automation that they want to provide, I generally believe that vision, or a camera and a radar, will find a place from the cheapest car to the costliest platform. I'm not so sure about LiDAR at this point in time, but that's the way we look at it, right? It's, again, if I look at radar, the two fundamental advantages, the way they're being built right now is one, they're getting a lot more easier to install and maintain and manufacture, and a lot more cheaper in terms of system cost. So they would like to use the benefits even in a very basic segment of the car, and essentially it provides the accuracy which can take you to at least some extent of perception for providing highly automated driving.
Fantastic. Radhavan, I've got a specific question for you here. So in your presentation, you talked about low-level fusion at the sensor level. Do you see sensors becoming smarter, and thus we move to a highly decentralized fusion process?
I think that the trend was to actually move to a highly centralized processor for, especially for raw or low-level sensor fusion. So I don't necessarily. I think the direction is more centralized computing unit rather than distributed computing unit. But I wanted to just reflect on the previous question that just a moment ago Sandeep was talking about. wanted to say that I agree with Sudipto that the ultrasonic sensors are probably likely to go away. If radars and LiDARs become available on a vehicle, then there's no purpose for ultrasonic, because ultrasonic, they're very short range type of sensor, and they're not able to support the high speed applications or higher speed application other than maybe parking type of application.
Okay, great.
For autonomous features. Yeah.
Fantastic.
Sorry.
Okay, I think we're actually running out of time at this point, so my apologies if we didn't get to your question. Unfortunately, we have just run out of time. I'd like to take this opportunity to thank you both for your participation. I think our audience would agree we've had some extremely insightful presentations today. Just a quick reminder to everyone that the recording for this webinar will be sent out in the next day or so, so look out for an email from myself. And also, again, just a reminder regarding the ADAS Autonomous Vehicles Conference. If you found today's presentations interesting and relevant to what you do, please do check out this event. It will be further addressing the developments of sensor technology, consumer acceptance, the algorithms relating to autonomy, machine learning, and much more. But from me and from TU-Automotive HQ, that is everything. Gentlemen, thank you once again, and to audience, thank you very much for your participation today, and we hope to be in touch very soon. Take care now. Bye.